Hey, buddy.
Hey, can you hear me?
Yes, sir. Good afternoon, everybody. Hey, thanks for coming to the virtual lunch and learn today. I have everyone on mute, and as per usual, for those who haven't been on this lunch and learn before, if you have any questions, type them in the chat section, and I will ask them to Eric. I work to keep everyone on mute so that we don't have dogs and kids and other things in the background. I'm really happy to have Eric Parvin join us today. Um, Eric and I worked together a few years back at Halker Consulting, and really had a good relationship there. And Eric's gone on to open his own consultancy, Parv Consulting, where he is the owner over there. He also teaches a few other classes through different entities and is even working on some of his own, which I think he's going to tell you about a little later. So, Eric, with that said, man, let's get kicked off and looking forward to it.
All right. Hey, thank you, Adam, for setting this up. I appreciate it. What we're talking about today is fire case PSV sizing common mistakes, and we're going to go over a little bit about the most common mistakes that we see when we do cold eyes review when we're going behind other companies. Get this. A quick review of our company. A lot of people think we do a lot of specialty work in PSVs. It's not all that we do, although that is one of our specialties. We do offer PSV training. It's a one-day class. We're looking at throwing that into a two-day class. And we also offer fractionation train design. Our process engineering expertise does go all the way from upstream through refineries and chemical plants. It's very extensive in equipment design. If you want to know more about that, you can see our website, obviously. We also host process pop quiz topics on LinkedIn from time to time. We get a lot of feedback that people love that. If you want to see the past articles on that, there's a link here that you can access later, and a list of our current customers. Why the class? We have seen lots of errors found when performing independent audits of others. There's also been a lot of improvement in software in the industry over the last 10 years. For example, HYSYS Dynamics and their safety analysis tool built in is really good. VMG, the other simulating company that a lot of people are familiar with, they have a lot of PSV sizing tools in there as well. And there's a lot of other PSV software available. iPrism, PSPPM, Smith & Burgess in Houston has a good one called Salis that I don't have shown here. But in the end, we do encourage other EPC firms to join our class. It drives unity and consistency among all the firms that are offering to do PSV sizing. The last thing we want really is 3 engineers and 4 opinions on what size the PSV ought to be. And this especially we find is true with fire sizing. At the end of the day, no one wins. Because of this happening with one client, we have developed a PSV guideline for not only fire cases, but every scenario that's out there under the sun. And we also have another client that they actually tested 2 EPC firms to do flare header sizing for fire case and a few other things. And they ended up getting size between one size was 12 inches flare header size, the other one was 18 inches. And at that point, they just shook their head and said, no one knows what they're doing. We're just going to bring all this in-house. And then you lose a lot of expertise as well. So what we're trying to do is just drive unity and consistency among everyone that's doing these kind of calculations. One thing I want to point out that's usually a misunderstanding about PSVs and fire sizing is that PSVs don't necessarily prevent the tower or the vessel from yielding or exploding during a fire event. Here's a picture from the Port Neches facility. It's a rubber manufacturing facility down in Texas. About 12 hours after the initial explosion and fire, the tower eventually lit off and yielded and blew up. And you can actually see it here flying through the air on this picture. If you want to have access to this slideshow afterwards, the explosion that sent this tower into the air, people 52 miles away in Louisiana actually said the walls of their home shook. And again, it was properly protected with a PSV, but the heat of the metal wall temperature eventually yielded to the temperatures and the pressure inside. So please don't think that if you have a PSV on a vessel for fire sizing and it's appropriately sized, that you're not going to have an exploding vessel taken off. I also have in our training class several other events where people are filming a fire going on, the explosion occurs, and then the vessel literally lands about 10 feet to the left of them. It's really something to behold. Not a fun feeling, but if you see a fire happening in your facility, don't be comforted by the fact they have PSVs. You should just follow your procedures and get wherever you need to be safe. Another thing that we see in the upstream world is a lot of folks actually try to dismiss the fire case. And I'm going to say there's no one right or wrong answer, but the question comes up all the time. Can I dismiss the fire case? In short, if you're in a code compliant state, you have to follow ASME requirements. ASME says if there are no flammables around, you can dismiss it with appropriate multidisciplinary sign off. And there's some other requirements listed in the ASME code. A good example of this is like an instrument air receiver that's located maybe 500 feet away from any hydrocarbon source. Maybe you can, in that scenario, dismiss the fire case. If there's any flammables around, though, then the short answer is you need a fire case, period. You need a fire case on your PSV. We have seen several upstream clients dismiss the fire as not needing to size it, and that's just a corporate risk decision if they make that decision. Fabricators for heater treaters or other upstream common vessels, whenever we're trying to provide a nozzle for your PSV, very often the PSV is too small for the right size PSV. Special note here, fabricators are not necessarily responsible for sizing this. Sort of like if you buy a tower with an internal flange for your distributor pipe, the question is going to become who buys the gasket for that flange? The internal vendor doesn't provide it, the fabricator doesn't provide it. The owner is responsible for making sure that gasket is purchased and installed. Same thing with PSVs. The owner ultimately is responsible for assigning that task of sizing the fire case PSV as well as the nozzle size on the vessel to be appropriately sized. If you're in a code compliant state, you're on the hook to follow ASME. If you're in a non-code state, and we've heard this argument before, fire often gets dismissed by the corporate risk decision makers, but I would say please check your state's requirements. They do have available public interpretations that may still mandate following ASME if your vessel is a code stamped vessel, even though you're not in a code compliant state. So please check your regulatory requirements when it comes to installing a code vessel inside of a non-code compliant state. So let's get down to the equations, which is what a lot of people love. We usually have to determine first the heat flux into a material is going to boil. This is a very familiar equation. Your C factor for this equation for heat flux is 21,000 or it's 34,500. The environmental factor we're not going to discuss today. Your wetted surface area is the area inside the vessel where the liquid absorbs heat. Most commonly, we see Q is equal to 21,000 times the area to the 0.82 number. However, I want to highlight there's a lot of assumptions in that 21,000 number we want to just make sure people are aware of. It assumes, if you read through the API 521 document, that you have both good drainage and good firefighting techniques. So what we'll say here is a good example of where you don't have good drainage or good firefighting techniques is a remote well pad out in the North 40, so to speak. You have a little, looks like propane vessel here. You've got a vessel in here as well, and it's inside of a berm. There's no way any of this is actually designed for what we would call good drainage. The other thing that you also have to have is good firefighting techniques. In a refinery environment, like we see this satellite photo of here, you usually do have good drainage and you do have on-site firefighting techniques. If you have both, you can use the 21,000 number. If you're absent of either one of these numbers or either one of these assumptions, then you're required to actually use the 34,500 number. This is nearly a 65% increase in the heat flux calculation for what's going to be boiling inside your vessel. So please be aware, one of the common mistakes we find, especially in upstream, is that people are just on autopilot using 21,000 when they should be using 34,500, and they underreport the area required by over 60%. Also want to highlight the wetted area factor is a common area where we find mistakes that are made. The liquid level that you assume inside your vessel, oftentimes people just assume the high liquid level, they're on autopilot and they just move on. What level do you have to use? API 521 provides some good guidance on this as well. There's a few references here you can look at later. For example, in towers, you can use the normal liquid level plus the height of all the liquid on the trays above. For working storage, they actually recommend using maximum liquid level. In a heater treater, I actually like to use whatever liquid level is there from the internals. It just depends on your vessel. But if you can use the normal liquid level, for example, on towers, instead of the high liquid level, you can have a significant reduction in the amount of wetted surface area that you would have and reduce your PSV size required. Another thing that's commonly missed is people will include the heads inside of skirts, say for example on towers. API gives you a get out of jail free card right here in this reference saying that you can neglect the area of the bottom head inside of a skirt. Reason for this is that you don't usually have good air circulation inside, and impingement of the flames on the head in the skirt is minimal, so you can dismiss that wetted area. We see that forgotten many times, so I would say that's just another mistake we find. Another thing that should be considered that we don't detail out today is that API says you should consider the amount of piping that's attached to your vessel for additional heat flux into the system. However, it does not say shall. It says it should be considered. Shall indicates that you're recommended to include, so up to your engineering practices whether you want to include that or not. Rarely also noticed in API 521 in this section is the fact that if your vessel is in a confined area, for example, heater treater is inside of a small building to protect it from the weather elements. We see that in Colorado and North Dakota, other places as well. Let's say that you have several pieces of equipment inside of a compressor house and you have vessels inside there. Your wetted area calculation now, instead of raising this wetted area to 0.82, API says it should be changed to an exponent of 1. This does greatly increase the heat flux into the vessel as well, and it's a common mistake that we find, especially in upstream and inside special areas of refineries. Let's move on. Another thing that we find is, say you have one PSV protecting multiple pieces of equipment simultaneously. We have seen on about half of the audits that we do going behind other companies, they'll actually add up the wetted area of all the vessels and raise it to the 0.82 power. The right way is actually doing each area raised to the 0.82 power and then adding up all those terms together and coming up with the right answer. On this very simple example we have here, it makes a difference of about 20% in your heat flux. So we have seen people actually miss the heat flux value in some cases by more than 30% when doing a independent audit. So make sure that this is a detail that's captured if you have a PSV protecting more than one piece of equipment. API has commented on this previously with inquiries, and they usually get the same inquiry about every 5 years. So it's not a common mistake to find, and it's something that API does address. They're adding language to this in a upcoming edition within the next year to clarify this in writing. So now we've gone over some of the heat flux issues. What's the next thing we do? Very commonly, we just say the heat flux divided by the latent heat, and that gives us the mass flow that we need for the PS. One of the hot debates that we come across a lot of times from engineering company to engineering company is, what is the latent heat? At school, it's the energy required to change 1 pound of liquid into a pound of vapor. However, for a multi-component mixture, this becomes a little trickier, especially for a fire sizing case. So we always say, and we want to make sure that we're liberating 1 pound of material from the liquid to determine our latent heat. API discusses this actually in this section of 521, and it goes through a lot of paragraphs to actually say, ultimately, there is not a standard latent heat effect, but sometimes you have degassing or dissolution effects causing a higher latent heat than what your simulation property tab will tell you, for example. Also, there's a paragraph saying that multi-component mixtures have a wide boiling range, and that it might be necessary to develop a time-dependent model where total heat input to the vessel not only causes vaporization, but also raises the temperature of the remaining liquid, keeping it at its boiling point. In other words, you have sensible heat effects going into a multi-component mixture of liquid that's being boiled. So you actually need to consider the MCP delta T as well as the M lambda H. Most engineering companies look at just the latent heat effect, or your lambda, and they ignore this MCP delta T. Now, is it wrong? Not necessarily, but it's very conservative. It will drive people to have a much larger PSV than you may need. For multi-component systems that begin to boil, this term does exist. Here is an example of the latent heat in the red curve. This is using HYSYS, using the physical properties tab that's in the stream window, versus the latent heat that you would get if you considered sensible heat effects in the blue curve. And you see almost always, with a little exception here at the first little boiling point, almost always the latent heat, including sensible heat effects, is higher than the latent heat that you would get out of the property window. This is for an HD5 propane stream. And even with the stream being mostly propane, you do see this effect occurring going on. This specific example, the latent heat with sensible heat effects, is approximately 5 to 10% higher than the latent heat out of the property tab in your stream window. For multi-component systems, the other thing we need to remember is, as your temperature increases and you're boiling more material off, typically your PSV area required increases. But also, as your temperature increases, the latent heat reduces, so your PSV area required increases a little bit more. As your temperature increases, molecular weight increases, so your PSV area required according to this heuristics decreases slightly. As temperature increases, you're boiling off liquids, so guess what? The other thing changing is your wetted area is actually decreasing, so the heat input decreases, your PSV area required decreases. So you have a lot of moving parts that you need to try to consider simultaneously, and it's actually difficult to do by hand. So we're going to walk through some examples of what that would look like if you did try to do this by hand. Here's a very simple vertical cylindrical pressure vessel. If you look at the amount of material of your liquid boiled off versus the heat input, these are what the curves look like. If you were to look at the latent heat in the blue curve and the relief rate required in the red curve, you see you actually have a mass flow peak around the 15 to 20% mark. So that's a little bit hard to estimate by hand, but you can if you do a lot of work on it. Ultimately, though, what you're trying to go for is the PSV area required as you're boiling off that material inside the vessel. We tend to ignore the first 1 or 2% because the amount of liquid to be boiled off in order to bring the vessel to overpressure is would usually consume up this first little bit. In this case, our peak looks like it's around the 15% mark. However, we have seen curves that look like this, where your PSV area required peaks out usually somewhere beyond the 20% mark. This green curve, I have the example of here shortly. We have come across this in refineries quite often, especially on diesel systems, where your area required peaks at somewhere between the 30 and 70% mark of boil off. So please understand, if you just make a decision, or your contracting firm makes a decision just to use the 10% mark for boil off, you might be missing the peak area required. So how do you actually determine that? There's 4 popular ways we've seen in the industry over the last 20 years. Your liquid property tab is the most common one we see. So condense it, that's this method. If you have hydrogen or very light hydrocarbons, then you actually get a lot of sensible heat to bring that very light hydrocarbon to its bubble point, to its liquid condition. If methane's involved, you're talking negative hundreds of degrees. We've seen people set up 100 drums and 100 latent heats. We don't show that here. It's very tedious and requires a lot of time. You can also set up a case study with 1 drum and actually walk through the procedure that we have here. This picture is available to you if you want to geek out on it and try and set this up later. And that's what we call method D. That is our preferred method in order to determine the true latent heat for a fire case. The other thing that we want to point out is with methane concentration, which is very common in the upstream world, your latent heat that you would get by the method D, the one that we're talking about here, is going to be very, very different between method A and B. Your physical property tab to take a pound of the entire liquid and vaporize it is going to tell you, in this case, 167. The vapor being liberated and then recondensed is going to tell you 394. These are 2 very different numbers, 2 very different approaches. Whereas the number that we come up with, it says 2,500, which is a lot higher than water. So immediately a lot of people are thinking, wait a minute, that's just got to be wrong. But in reality, it's actually correct, because remember, you're fighting dissolution and not necessarily a true latent heat. So your curve across the entire boiling point range is going to look like this when you have methane involved. Now, why is this important to know? For sizing a PSV, for example, on a heater treater or anything in the upstream world, this dissolution effect is significant. It can actually cause you to have a much, much smaller PSV than what some EPC firms will tell you to do, especially if you're using the property tab window out of the simulation. As you get down here to the 50% boil off range, I mean, you're off by about a factor of 3 or 4. It's a significant difference. So definitely consider this if you're seeing large PSVs being cranked out by your EPC firm you're using. Let's shift to gasoline range material. How different is the effect? In this case, not as different, but it's still about a 15 to 20% difference between using the physical property tab and actually calculating the sensible heat effect. So, or methane solubility, if you have ethane, like in a fractionation, still is a big difference, especially in the first 10 to 20% boiling point range. How do you review this detail yourself? A few options in the industry do exist. HYSYS actually has a really good safety analysis tool. You can program a PSV, put in the properties for set point and all that. So long as you don't cross the supercritical range, and HYSYS defaults at your compressibility factor being less than 0.8, you can run a semi-dynamic analysis. So you actually just tell it vapor, semi-dynamic analysis. You click on the edit flash table, and you actually get this report. And see, this is for diesel. For the first 10%, which is where a lot of companies just stop for evaluating the fire, you get an area required of 0.36 inches squared. But really the controlling point is the 60% of the material is boiled off. It happens an hour and a half after the fire starts, but it's your maximum PSV capacity. We actually go a little bit past the J size PSV according to API sizing. So this is the kind of tool available to you out in the market. It's very easy to use. It is relatively intuitive. PSPPM software by Siemens also has a good version of doing the same thing as HYSYS. the more recent versions, use it in 2 years, you're probably not used to seeing. We do want to make sure other methods that you can determine by very carefully. Salus also has a good tool for doing semi-dynamic analysis. VMG can perform a more rigorous, fully dynamic analysis to flare systems and is a good tool as well. In fact, in VMG, I think you can light off 3 vessels simultaneously so you can evaluate your flare header. iPrism has a similar function. However, it's extremely conservative and it requires some manual intervention for you to get the right answer. So I would say if you're using iPrism, please use it with a grain of salt and do some quality checking on it. It doesn't consider, for example, the reduction in wetted area as it goes down, or at least not that I'm aware of. And I've never come across a client that actually knows how to look at that properly to reduce the wetted area while the fire goes on. It does a good job evaluating the other physical properties, but be careful in believing its final result without doing some scrutiny on the results. A couple other factors to consider for liquid-filled vessels. It became popular in the 90s to say that you have to eject 2-phase fluid through the PSV. So people were cranking out these Mongo-sized PSVs. Research later concluded in the 90s that you don't necessarily need to do this so long as the PSV inlet line is at quote-unquote a high point from the source of vapor generation. So what happens is that you generate some vapor, which is causing overpressure, but it goes to a high point, and if it's sitting right under the PSV nozzle, then you can assume that it's going to eject vapor and not a 2-phase material through the PSV for sizing. However, if the PSV is installed at a low point from the vessel, and this is popular with heat exchangers so that the PSV is accessible, then API says you should design the PSV to relieve the same volume of liquid that is equivalent to the vapor expansion that's being generated inside the vessel. If you want to see more details on this, there's the API reference as well. This is often called liquid expulsion. Other examples that are going to be common in almost every facility, liquid-filled filters with the PSV coming off the side of the filter, and PSVs protecting heat exchangers with the PSV off the bottom of the heat exchanger piping. We have seen this quite commonly. What's the failure here? If you don't size it for this liquid expulsion case, your PSV size required is typically 3 to 4 times larger than just having the vapor go through the PSV. So please, with the installation details, remember to consider this. If you want, here's a checklist that we developed for Flux. We also have some checklists on other things, but this is a good little QAQ we've talked about today. And with that, we've only scratched the surface, but we wanted to see if anyone has any questions about fire case or anything else. Adam?
Eric, thanks so much. Really appreciate the information and time. I'm going to give people a minute or two to see if they type in any questions here. Otherwise, if we just want to, move along, let's give them ways to contact you if you wouldn't mind.
Yeah. Yep. On our website, we have a contact, and then also it's just eric@parvconsulting.com. Very easy to remember. So if you want to reach out to me, I love taking phone calls. I love taking emails. It's no problem at all. I take it from people on LinkedIn as well from time to time. So if you ever have a question after the fact, please feel free to call.
One question popped up, if we're able to get a copy of the presentation, PDF or other. Answer to that question is yeah. I'm going to post this video online. And then also Eric did provide a copy of the presentation. So if you want to contact he or I on LinkedIn, we'll go ahead and get that presentation over to you. There's another question about an HYSYS example of the PSV flashing. Khalid, let's for that, let's go ahead and just contact Eric direct on LinkedIn, and you guys can have a conversation over the phone. we put together this presentation just sort of generally to give some overviews, but I'm sure Eric, correct me if I'm wrong, but I think Eric's willing to dive in
Yeah.
any questions that you might have there. So I'll let you guys connect offline. Anything else, guys? All right, Eric, thanks again. Everyone, thanks for joining. I'm going to try and do another one next week, and we'll see what kind of topics we can come up with. If anyone has any suggestions, please feel free to email me or contact me on LinkedIn. And trying to get the most information that we can out there right now while everyone's kind of at home taking advantage of these Friday afternoons. So have a great afternoon, guys. Talk to you soon.
All right.